Hello everyone, welcome back to more formally verifying within Rocq. So to cover what we did last time, we created this module node ordered, and we used that to create a set of nodes so that we could augment our graph with sets instead of lists of nodes. Then from there, we were able to define the down here we have graph induction. See what type this is. So graph induction, it has any proposition P that ranges over graphs. Then it has the hypothesis, the induction hypothesis, where if we know for all strict subgraphs that P holds, then we know that it holds for all graphs. We defined strict subset to be everything is contained within one, but not everything is contained within the other. And we managed to prove this graph induction property. So let's get down to the final theorem that we want to prove. We want to prove that for all graphs, we're trying to figure out a path between A and B, and A and B are within the graph itself. We want to find that there's either a path between A and B, or there isn't a path between A and B. I actually think these two hypotheses are maybe not required, but I'll leave them in there for now. So let's try to use our graph induction property to do this. So that we're not going to be able to prove this right away today, but we're going to see why we need to do the things that we need to do right now. So I introduced just the G so that I can leave this abstractly over A and B. And now we want to do induction. Using our graph int. I think this is going to complain. Yep. And it's basically saying that we want something that is from graph to type and not graph to prop. So let's go ahead and change that. And thankfully, the way that we defined it, this still works. Now we jump back down here and we have our induction. Let me change the name of this X. There's two assumptions in here, so I named them G and IH. Yep. So here we want to prove that there's a path between A and B inside of G. Like we can determine whether there's a path A and B. And we have our induction hypothesis that for any strict subset of the graph, the G prime, we can query whether there's a path between any two nodes within it. So this is how do we take this induction hypothesis and get to this conclusion? This is the last step we need to do for our proof. It's a very big step, though. So the main idea is we can uniquely determine whether there is a path by starting with A and finding all of the edges that A goes to, so like the nodes that our neighbors to A. So search through the edges, find the edges that start with the two of the from of the A, and for each one of the twos, check whether there is a path from that two to B. Or there's also the possibility that we immediately find an edge between A and B, in which case we are done, we have found it. But we could also filter that out. So the main node that we're taking off is the A, like the starting node. We're finding all the edges that it connects to, and we're removing those edges, and we now have a subgraph where we are going from a neighbor in a smaller graph to the B. And so with that, the induction hypothesis is able to carry us through. We have removed this particular node, so we know that there's a way to determine whether there is a path or not. And we need to be able to take a path from that subplot and move it up into like the larger graph. So I will write down a few things that we need to do this whole proof. So first of all, we need a algorithm to remove particular node. Yes. Then from this algorithm, we want to prove that we can put it into this function, this induction hypothesis here. So that requires proving it is a graph and proving it is a strict subset. First, prove algorithm gives us a graph. And then prove algorithm gives us strict subset. And from there, we're able to determine whether we have a graph in the smaller graph, the G prime. So we would like to take this path within the smaller one and bring it up to the bigger one. So we can prove that for the Yep. And there might be difficulties with proving the negation component. We'll get to that later. For now, we do have a few steps that we want to do, and this might take us the whole video. We might not even finish. So we'll start with the algorithm to remove particular nodes and edges. So we essentially want to remove this first node A. We have the node, so we can just remove it from the set of nodes. But we also want to remove all edges that mention A. So we need to do a filtering through the list and list of edges and remove anything that mentions A. So definition, or rather, let's see the function that we're going to be using. Module S. And in here we see this remove function. It takes in an element and a set and gives you back a set. So let's search what lemmas are associated with s.remove. And here we see for any set S, X and Y, if we're stating that Y is in this remove XS implies that Y is in S and Y is not X. So I guess it means that the if X belonged within S, then it was removed from the set because of this extra condition of Y is not equal to X. So that remove is exactly what we want for the sets. And we want to prove so remove node from a graph, and we want to return a graph. And this is a node. And I guess we don't need to prove that it's within the graph for the definition. Apply make graph. Yep. So we need to provide it the set of nodes and the set of edges. So here's where we do our filter. So the first thing is going to be the set of nodes, and that will just be s.remove n from the nodes of G. I'll still complain because we don't have any edges. But now we also filter the edges, and we'll do we'll use this function, list.filter. It for any A to Boolean, it takes one list A and converts it into another list A. So I think I imported this filter sufficient. Yep, filter. So we have a function from A, which is going to be an edge. And we want to return a, we also put in a list. So that's going to be the edges of G. And now we just need to implement the function inside of here, filter out the G. So filter is going to, I believe, keep the ones that are true and remove the ones that are false. So we'll check that for the particular node if if the in E the from and to, if from E is equal to n. So how do we check if it's equal to? We have the citable equality up here, equal dec from node ordered. So if node ordered equal dec from E to E is equal to n, then false, else 2e is equal to n, then false, else we keep it. Yes, we have edges to bool. Okay, so we did not use a list for the edges, which is actually a good idea. We used a function from the edges to bool, so that makes it even easier. We don't need to use this filter function. Instead of true, we just check whether it's an edge in the bigger graph. Yep. Cool. And that pops out all of the things that we need to prove about it. I haven't tried proving any of these yet, so I don't know how hard they're going to be, but get started. So this first one, expand it out a little bit. We have this large if statement that we wrote over here, and we want to check that for any edge, as long as this is true, then it is in the remove n from E is within remove n nodes G. Basically that it is closed underneath the nodes. The edges aren't pointing to things outside of the graph. Let's just try it out. Intros E and HE. Cool. Then we do have the function that takes us from s dot in of the remove into the other thing that we wanted. Let's check filter up here. We search s dot remove. We have this s dot remove spec, and it takes us from something of this form into something of that other form. So let's try doing those rewrites. That worked. Let's do it again. Yep. So we do know that this condition and this condition are true as long as it's within the edges of G, E. And these are just filtering to false, so they could never happen. So we at least know that the edges of E is true. So let's try destructing on this a little bit to get out that we have the edges of E being true, and we have these other two statements being impossible. So the way to do that would be destruct. Take this here. H1 or H1. So this is going to give us in this first case here, we have false equal to true, which is impossible. So, contradiction. Oops. Not contradiction. Discriminate HE. So now we know that the node order.eq from me end is not true. We can even do an unfold node order.eq and h1. Hopefully that works. Yep. So we know that from me is not equal to n. And we can do this again over here. So I'll just copy paste all of this and change it to a 2e. And I'll call it h2. We once again enter into this case in here where false is equal to true, which cannot happen. So we are assured that it is not equal to. So we can unfold that definition of EQ in there. And we have that edges G, E is equal to true. And we check our definition of graph, we should have a edges closed function, which we should be able to use here from edges GE. So apply no closed in HE. Let's see. Oh, what's it called? Edges closed. Edges closed. And so we have these two components here. And so now we actually have all the components that we need, that E is not equal to N, the from and the twos are not equal to N, and then we have that the ins, so destruct HE as 3 and H4. And hopefully this is done with auto. Yep. And from that, we have cleared the first thing that we need to prove about it being a graph. So now we get to the next thing that we need to prove. Let's take a look at the definition of graph again. So this next lemma is that there's no self-edges, so that if edges E is equal to true, then from E is not equal to 2E. So we'll do a very similar process as before. We see that it looks very similar. And we should be copy paste most of this proof, and we should be good. Of course, we're not going to be rewriting this anymore. We do these intros, and then down to here it should be exactly the same. And now instead of edges closed in HE, we can do the no self edges. In HE. And that's exactly the lemma that we needed. So we just do auto. That was pretty easy. Of course, we're copy pasting proofs over again, so sometimes it's good to do a tactic, create your own tactic to not copy paste over and over again. But it's a short proof, and there's small differences, so might as well leave it. And then for this last one, this proof corresponds to undirected, basically stating that we can flip the edge. And so we do need to prove that the flipped version of this is not in the list. So we can do like simplification here actually. Simple. Yep. So it's from and to and to and from. But they are pretty symmetric in every way, so this should be easy to prove. And we'll start it off exactly the same way as before. Then that actually solved both things for us. Because when I did this first destruct, it's actually pretty funny that it worked out this way. Uh, this from here was the first one over here, but it was the second one over here. So when we did this first destruct, we got down into here. It destructed the first one of this HE, but it destructed the second one from this bottom part. So it's nice that I was able to do that. I wasn't expecting it to work out that nicely, but I guess it did. And then of course the destructing that last part destructed it in both places. Then we just need to take these edges here and convert it into these edges. So the name of that theorem was undirected. So I think apply undirected should be fine in this case. Yep. And we should have HE product. And we are done. Find. So with this, we have a remove node algorithm that removes a particular n from the G. Then it removes all the edges associated with that n from the G. And we prove that it is a graph. Let's look back at our list of steps. Of the algorithm to remove the particular nodes and edges. That is done. That is these two components, the remove and this thing that filters out these two cases as false. So that one is done. And we need to prove that the algorithm gives us a graph. And that is also done by the fact that we prove that that this thing returns a graph. And we had to do all these steps here to prove that it was a graph. So it's just like, this is just defining the algorithm there, and then we need to prove that this entire thing is actually corresponding to the graph. So that is also done. Cool. So the next thing to do is prove that it gives us a strict subset. So let's state that as a lemma. So strict subset remove. No. So for any graph G and a node N, I guess we should take these as if we know that the s dot bin and nodes of G, so we are actually removing something, then the strict subset Is it called strict subset? Yeah. Then the node is going to be a strict subset of the strict subset remove node and G of this graph. So the nodes of this graph are going to be a strict subset of the nodes of G. Let's flip remove node Gn. Maybe that shouldn't be flipped or the other way. Small change. Yep. So now we do intros Gn Hin, and we need to prove that it's a strict subset of the node. And for here, we're actually going to, can we do simple? Simple? Yep. It converted it into s dot remove n nodes of G, because that is exactly how we defined the nodes of the remove. So it extracted this component here. Then what we need to do is if we unfold strict subset, there's two pieces that we need to prove. It's a subset in one direction and not in the other direction. So we'll actually just do a split instead of an unfold. So we need to do these two different proofs. And of course, the first proof, search s.subset. We have our two lemma statements here. Are either of these useful? Yeah, I guess this include one that we defined in the previous video matches up to what we want. Then intros H. We want to intro something that's not n, so I'm going to call it m, and h in m. To distinguish this, I'll call this h in n. So we now have that we have an element m, or basically a node m, and it is in the elements of s.remove. So we could change this search in and s.elements. I guess we need an additional lemma here. That in the elements is identical to s.in of the element. Let's actually change this subset incl to not expose the s dot elements. We want a lemma subset in. So s dot subset s1 and s2 if and only if s dot for all x in x s1 implies s dot in x s2. So this is the lemma that we'll want to do to convert this s dot subset into what we actually want. Oops. For all s1, s2, t. Instead of subset incl, we'll do subset in and converted it into this form. Intros m and h in m. That is now the form that we want it to be in. And we can do a we see that now it's in this proper form for this remove spec, so we can rewrite it in h in m. So rewrite remove spec in h in m. So now we have these two components here, and we only really care about this first one. So is this result with R? Nope. But it is resolved with apply h and m, I believe. Yep. And since we split it, we now need to prove the second side of this. So intros h. I'll call it h sub. And now we do a rewrite with the subset in. And we want to specify that n is one of the nodes in G, and it is not within this. So we can actually apply h sub into h in n. And gets this thing in here. And we can do our rewrite with the remove spec in h in n, and gives us that n is not equal to n, which is impossible. So we should do apply h in n to our goal, because this one is defined as this implies n is equal to n implies false. So we just need to prove that n is equal to n, which is true by reflexivity. And we are done proving that it is a strict subset. Although we did create this helper function in there, we could prove it right now if we wanted to, but we're sort of assured that this makes sense. So I'll leave it there for now, and we'll look at the other stuff to do. I'll add it as a feature to do. Prove subset in. So we now have proved that the algorithm gives us a strict subset. And now we want to prove this final part, that if the this remove node from the graph gives us a path, then we should have a path in the larger graph between those same edges. So let's do that lemma. Remove node path for all G graph A and B nodes. Node. If we have a path in, I guess I should do a remove n. N is the node. Remove node of G. There's a path within remove node of G from A to B. Implies there is a path in G from A to B. So intros G and A, B. And for here, this might be tough. We want to do basically a dependent induction on this path. Let's do an intros of this path P. We basically want to prove that there's a path from A to B in the larger graph by doing induction on how this path here was constructed and using that to construct the other path. Let's try doing induction P, and hopefully, okay, it is actually working. So induction P, and we'll give it the node. So this first one is going to be 8A and edge. Then the second case, I'll just leave it blank for now. So in this first case, we have we know that A is within the nodes of remove node of G. So we just need to state that there's a path from A to A in G. So search path. What's the name of the path REPL? What we want here. Now we just need to prove that there is an A in the nodes of G. And if we do the simplification in here in the each edge, we'll see that the nodes of remove nodes get simplified to s.remove n. And then we can use this rewrite spec again. To get us that the thing that we need. I'll call it just H instead of H edge. A little misleading. And then within the second, like the transitive component of path, uh, I want to rename a lot of these things. So we'll call it an A and an E and H of E and P and IH. So that just changed all the naming. So we know that the edges of remove NGE is equal to true, and there's a path in there, but our induction hypothesis tells us there's actually a path here. We don't really care about this path over here. I think we can even do an underscore here because we don't care about that path. Yep. So we just need to prove that there's a path from A to E. And to do that, all we need to do is state that E is an edge within the larger graph. There's a path. It's a bit hard to find in there. Let's just look at the definition of path directly. Path edge is the constructor that we want to use in this case. So if we apply path edge, we need to know that there's a path from A to from E, which is the one over there. And we want to know that the edges B is equal to true. So we deduce that from this top one. But auto will clear out the second goal, so let's do that. So we have just left with this one. And we'll try simplifying within here. In HE. And we get this gigantic statement here again, but we see that the edges GE is equal to true. So if we do a couple of destructs, destruct and try discriminate HE, then we get this thing here that we don't care about, and our HE has been simplified by one step. Change this to a 2E instead. Then we get out our desired thing in here. So exact HE. Cool. And with this, we have proven that if we remove n, or whatever n, then a path within the smaller one is going to be a path within the larger. So combining these things together, if we were to try to solve this part here, so we can go ahead and try to do that. Controls A, B, H A, H B. We want to prove that there's either a path here or there. So let's check whether there's a path in this bottom one. So we want to show that for the removing of the A graph, we are able to check whether A and B for like any two A and B nodes are within the graph. There's a path or not. So copy this thing here. Or let's do this thing. Assert strict subset remove node of GA or of we are asserting the statement that the remove nodes is a strict subset of the nodes in G. And the proof of that would be by strict subset remove node, which is a lemma that we proved. So we are done. Oh, we also need to know that it's A within, so auto. And that closes off our proof. H remove, then call it H remove instead of H. Then we can apply IH in HREM. For I guess we don't know right now what the edges of A and B are, so we basically what we're missing here is a means of deducing that the if there is a path, it needs to have gone through one of the neighbors of A. Otherwise, it could not have that there could not have been a graph. And so I don't really know what A and B I need to be plugging in. I know the B corresponds to this B, but A would be a neighbor of A, assuming we're constructing paths from the left side. I think the definition, we're actually constructing paths from the right side, so maybe I flip it and find the neighbors of B instead of the neighbors of A and build backwards. But they should both be valid because we proved all the properties about paths. So yeah, I guess I'll still keep with the neighbors of A. That's more intuitive. So we need to search through the neighbors of A and apply induction for each one of those. But so the statement that we want here is G prime being the removed nodes. And here we do intro apply IH. Oops. I need this to be a different A than the one that I'm removing. Yep. So A prime is a neighbor of A, and we know from our induction hypothesis that this path here that we can determine within the remove node G whether there's a path from within any two nodes A prime and B. So I guess I'll just move this part of this proof into here. Yep. And I did state before that it's probably possible to remove these two statements, so that does make my life easier in some ways and harder in other ways, so I'll do that. Hopefully makes it easier and harder. Trails A prime B. Oh, I guess first of all, uh, I want to find that s dot in is decidable. I'm not finding it right now. We want an additional lemma that says nodes decidable. For all G graph and node, we can uniquely determine whether the the s dot in and nodes of G, or it's not within it. That's another to do. So we will destruct node decidable on A as HA, HA. So decidable GA. So in the first case, we know that it's in it, but in the second case, we don't know. We know that it's not in it. So we'll actually go ahead and do the proof here because we know that there can't be a graph, a path, because we know it's not even in the graph. So the right side, and then intros P, and induction P. Here we have a median contradiction. So I'll do auto. And the other one was also pretty much a contradiction, so it completed. So assuming that we have a way of deciding whether it's in the set or not, which should be true. Then we know, like, if it's not in the set, there is no path. So we have left to prove that it is. We know that it's in the set. We need to prove that there is a path. So this final statement here now complete. I'll call this IH prime as IH, or actually HREM. I'll leave this one as IH. Now it is named HREM. So within the remove node subgraph, we know that there either is a path or there isn't a path. Let's try. I think this will break. Yeah, this is just proven as one arrow. We need to prove the opposite direction of that arrow as well. And that might be a bit harder. What assumptions do we need to prove the opposite direction? Well, namely that the connection between A and B could not have gone through N itself. Okay, this might be, like, proving the opposite direction of this is going to be a more complicated statement to make. And I'll probably leave it to the next video. But for now, we have, I guess we did prove this final part. We created an extra lemma here, nodes decidable. And we'll have to figure out what lemmas we need to finalize this proof. We need a way to extract all the neighbors of A and put that in to this HREM as A prime to figure out whether there's a path or not a path. And we want to convert from this path into this left side, but we also want to convert from this path into this right side. So this left side is the one that we've already completed. The right side to this right side is going to be a lot harder. Specifically because the direction of the arrow, this remove node path, since these are negations, the direction of this arrow is flipped. We will have a path from ng from A to B, and we want to prove that there's a path within remove node A, G, A prime of B. And that is because we need to quantify it so that the path from the if we choose every single edge connected to a particular node A, then we never need to visit A ever again. So if there is a path from A to B, we could have found a path that doesn't travel through A. If there's a path from A prime to B, then we could have found a path that doesn't travel through A. Yeah. that's going to be hard. I will probably do some work to figure out what exactly that proof statement is, but that should be the final statement that we need to do to prove this path decidable. And yeah, so thank you for watching, and I'll